Semaglutide. Your gut produces a hormone called GLP-1, glucagon-like peptide 1. It releases after you eat, travels to the brain, and tells it two things: stop being hungry and slow down how fast food moves through the stomach. GLP-1 is a short-lived signal. Enzymes in the bloodstream destroy it within minutes. So researchers asked a simple question: what if you built a version that survived longer? Semaglutide is that version. It mimics GLP-1 but remains in the bloodstream for around 7 days. The brain keeps receiving the stop eating signal. Not because you ate, because the molecule is still circulating. Clinical trials showed an average body weight loss of 15% over 68 weeks. That number had not been seen before in any non-surgical weight loss intervention. Ever. The mechanism is not complicated. Less hunger means fewer calories consumed. The body pulls from fat stores to cover the deficit. The peptide does not burn fat directly. It changes what you ask for. The side effects follow the same logic. Slowing gastric emptying means nausea, constipation, and vomiting in the early weeks as the dose climbs. The gut is processing more slowly than it expects. And here is the trade-off that defined the next 5 years of this research. Somewhere between 25 and 40% of the weight lost on semaglutide comes from lean mass, not fat, muscle. The compound does not distinguish. Tirzepatide. Tirzepatide targets two receptors, GLP-1 and GIP, glucose-dependent insulinotropic polypeptide. GIP receptors live inside fat tissue. When GIP signaling is active, fat cells become more metabolically flexible, less inflamed, more willing to release stored fatty acids. Paired with GLP-1 appetite suppression, the combination produced weight loss figures that outperformed semaglutide in every head-to-head comparison. Around 20 to 22% of body weight over 72 weeks in the strongest trials. The muscle loss problem did not disappear, but the GIP component appeared to blunt it at a modest level. Side effects stayed similar: nausea and gastrointestinal disruption, slightly reduced compared to pure GLP-1 agonism. It was sold as Mounjaro for diabetes, Zepbound for weight loss, and it raised an obvious question: what happens when you add a third receptor? Retatrutide, 3 receptors: GLP-1, GIP, and glucagon. Glucagon is the signal the body fires when it needs energy fast. It tells the liver to release glucose. It tells fat cells to break stored fat into circulating fuel, a process called lipolysis. In normal physiology, glucagon and insulin move in opposition. When one rises, the other falls. Retatrutide activates the glucagon receptor while suppressing appetite through GLP-1 and improving fat cell metabolism through GIP. The theoretical effect: the body eats less and burns more at the same time. Appetite suppressed, metabolic rate elevated, fat cells primed to release stored fuel. Phase 2 trials showed a 24% average weight loss at 48 weeks. Nothing that has reached Phase 3 has replicated that number. It is still in clinical trials. The glucagon receptor always raises the same concern: activate glucagon, and blood sugar rises. Retatrutide manages this by pairing it with GLP-1, which restores insulin sensitivity and prevents the glucose spike. Whether that balance holds across diverse populations at scale is what the remaining trials are testing. It is not legally available. Everyone using it right now is doing so outside clinical settings. The underground peptide market moved on this well before the approval process did. AOD 9604. Growth hormone does two distinct things for body composition. It builds tissue, and it breaks down fat. Those two functions come from different regions of the same molecule. AOD 9604 is the amino acids 177 to 191 of growth hormone. The fragment is responsible for fat breakdown, isolated and synthesized without the rest of the molecule attached. It activates beta-3 adrenergic receptors inside fat tissue. This triggers lipolysis, releasing stored fatty acids from fat cells into the bloodstream. At the same time, it inhibits lipogenesis, the process by which the body converts surplus calories into new fat storage. What it does not do: raise IGF-1, carry anabolic signaling, affects blood sugar, produce the receptor downregulation seen with full growth hormone use. Animal studies showed strong results. Human trials showed modest results. Metabolic pharmaceuticals ran Phase 3 trials for obesity and did not hit statistical significance on primary endpoints. The compound has no FDA approval for weight loss. The biohacking community uses it anyway. typically 250 to 500 micrograms daily, usually paired with CJC 1295 or ipamorelin. The reasoning: it targets fat specifically without the water retention, insulin resistance, or tissue overgrowth that full GH carries. Tesamorelin. Tesamorelin is the one peptide on this list with actual FDA approval, not for general weight loss, specifically for HIV-associated lipodystrophy, a condition where antiretroviral medications cause abnormal visceral fat accumulation in the abdomen. It is a synthetic version of growth hormone-releasing hormone, GHRH. It does not deliver growth hormone directly. It tells the pituitary gland to produce more of its own. The pituitary responds with a natural pulse, preserving the normal physiological rhythm rather than overriding it. Clinical trials in the approved indication showed around a 15 to 20% reduction in visceral adipose tissue over 26 weeks. Visceral fat specifically is the deep fat wrapped around organs. Subcutaneous fat responds far less dramatically. The effect appears regionally concentrated around the abdomen. Downstream, growth hormone raises IGF-1, which drives fat mobilization from visceral depots. Side effects include fluid retention, joint pain, and glucose elevations. Off-label use in the longevity and body composition community is extensive without the regulatory monitoring that the approved indication requires. CJC and ipamorelin. These two are rarely discussed separately because they are rarely used separately. The reason is mechanistic. CJC 1295 is a GHRH analog. It tells the pituitary to release growth hormone by mimicking the body's own growth hormone-releasing hormone. Long half-life. Sustained GH elevation across several days from a single injection. Ipamorelin activates growth hormone secretagogue receptors through a different pathway. Sharp, pulse-like GH release within minutes of injection. Its main advantage is specificity. It does not meaningfully elevate cortisol or prolactin, which older secretagogues consistently did. Together, CJC 1295 creates a base elevation of GH, while ipamorelin creates a peak on top of it. The combined output exceeds what either achieves alone. Neither peptide acts on fat directly. Elevated GH stimulates IGF-1 production in the liver. IGF-1 promotes fat oxidation, inhibits fat storage, and supports lean mass preservation. The body composition changes happen downstream of the GH signal, not at the peptide receptor interaction itself. This matters for managing expectations. CJC 1295 and ipamorelin do not produce the appetite suppression or the metabolic rate elevation of the GLP-1 class. They support a favorable body composition over months. The audience for them is people optimizing body composition who are already lean, not people with significant weight to lose. 5-amino-1-MQ. 5-amino-1-MQ is not a peptide in the traditional sense. It is a small molecule that blocks an enzyme called NNMT, nicotinamide N-methyltransferase. NMT sits inside fat cells and acts as a metabolic brake. When NMT is active, it consumes SAM, a methyl donor needed for energy-producing pathways. High NMT activity in fat tissue tracks with obesity, metabolic syndrome, and reduced fat cell metabolism. Block NNMT and fat cells shift into a higher metabolic state. They burn more energy. They proliferate less. In animal studies, they start behaving more like brown fat, which generates heat, and less like white fat, which stores calories and sits still. Human data is thin. The mechanism is compelling. It is taken orally, which distinguishes it from almost everything else on this list. No injection required. The compound is used widely in the research peptide community without any clinical trial data in humans to draw on. MOTS-C. MOTS is a peptide encoded not in nuclear DNA, but in the mitochondrial genome itself. That distinction surprised researchers when the compound was identified in 2015. Mitochondria, the energy-producing structures inside cells, turn out to have their own signaling molecules. MOTS appears to act as a signal from those energy factories to the rest of the cell and to distant tissues about metabolic state. When energy demand rises, MOTS production increases. It travels to the nucleus and activates gene programs that improve glucose uptake, fat oxidation, and cellular stress tolerance. In mouse studies, injected MOTS-C reversed diet-induced obesity and insulin resistance. It raised exercise capacity. It activated many of the same pathways that physical exercise activates at the gene expression level. The phrase exercise mimetic gets used carefully here. The animal data is what it is. Whether those effects translate to humans at clinically meaningful doses is not established. MOTS also declines with age, which has drawn the longevity research community's attention independently of weight loss. Lower levels in aging populations correlate with metabolic decline. Whether supplementing it reverses that decline is still an open question. What this class represents, 5-amino-1-MQ and MOTSC and compounds like them, is a different theory of fat loss entirely, not appetite suppression, not hormone manipulation. The premise is that you can change how efficiently fat cells use energy at the level of the cellular machinery itself, and that this change produces real body composition effects. The animal data are consistent. The human data does not yet exist at the scale needed to confirm or dismiss it. That is exactly where the research is going.